There's fundamentally nothing really new in this talk. It is just a compendium of things techniques that I've encountered or heard about, or that other people have told me about that have appeared in various APL systems through the ages. And I just thought it'd be a good thing to get these written down so it's something more than just mythology. And that was the purpose of this talk. So there's a draft paper available, which I think we'll probably get to eventually. I want to start with pardon the expression, a bit of introduction, because this talk is about Booleans. The interesting thing that I find is that the bit is the fundamental unit of digital computing, but computer languages, by and large, don't believe in bits. They believe in words, bytes, strings, and so on. But there's no way to deal with a bit except through indirection. So few languages support bits. Fewer yet support multidimensional bit arrays stored densely, and fewer yet provide array operations on Booleans. Or of the few languages that do support bit arrays, they're 1D, they're vectors only. So APL is quite a bit different in this regard, in that we do believe in multidimensional bit arrays. And of course, they appear in scan data, they appear in any kind of medical imaging things. You got dense arrays coming there. We're just talking about gray codes, things like this. They're everywhere. So the fact that APL has them is pretty good stuff. So these other languages leave the burden of dealing with them to bit twiddling that has to be done by the programmer, and that's inherently non-portable. It's also not fun. So APL, because we treat Booleans as the integers 0 and 1, makes life a lot easier. And since we have array-oriented operations, we can manipulate entire Boolean arrays just the way we manipulate other arrays. Why? So I asked Larry. Larry Breed was one of the implementers of APL16, the first production APL interpreter, and Larry was working, I guess, he was working for IBM at the time, and I asked him, where the one-bit Booleans came from, and I think he just thought it would be fun, little brain exercise. And so he decided to store Booleans densely, 8 bits per byte, in row major order. So just the same way we store other arrays. It made indexing, selection, and structural and selection verbs, and so on, all work the same way on bits of arrays as they do on other data. So a lot nicer. Now, of course, what this meant was this representation meant that indexing a single bit out of an array was more expensive, because you had to go and find the appropriate word or byte, grab that, mask off the piece we weren't interested in, align it properly to get that 0 and 1. So it's more expensive. But the thing is, it opened the door to these to SIMD Boolean array operations. Now, SIMD is a fancy computer science word. It means single instruction, multiple data. And this is what you get when you go 2 plus iota 5. Well, the plus is a SIMD operation. We're going to do plus on this vector of numbers. That's all SIMD is now. And that's what this talk is all about. So typically, the speed-ups were done either a character at a time, so you'd get 8 times speed up, or a word at a time on System 360, which would typically give you a 32 times speed up, but sometimes we did considerably better. So I think the important thing here is that Breed's design decision, it remains brilliant, because we can do so much in the Boolean domain. A lot of logic, stuff that would turn into if-then-elses, and cascading things, sets of if-then-else turn into just ands and ors. So it's good stuff. So the optimization, I think these optimizations are still relevant and important. And what's interesting that I will allude to a bit is that recent machine architectures, the new, we're talking about the AVX and SSE and all these things, they're starting to put very APL-like crude, but there are instructions in there. So for example, there's a Boolean compress available, and some other ones. They're starting to appear in machine languages, but they still don't exist in the computer languages that drive them. So some things are just continue to be weird. So Larry, having implemented these dense packed Booleans, he then optimized a lot of the scalar functions, the rank zero verbs. So all the traditional Boolean functions plus the relationals. When those were run on Boolean data, he would do a word at a time. So for free, you would, if you did one and, or maybe bad example, but but he would get a 32 times speed up on this just by doing a word of bits at a time. Simple, but quite effective. And then there were a number of us who optimized scalar extensions over the ages. And since these things were typically done by table entries or a little bit of code up front, they were not too expensive. So, for example, if I stumbled across a 1 and B, well, we just say, well, I'm not even going to bother with the itemized, the element-wise computation. I'll just return B and be done with it. So let's turn to strength reduction. This is a classical compiler optimization. And you replace a specific operation in a piece of code by another one that is somehow superior. It might be faster to execute, might have fewer memory references, or might be just more amenable to optimizations of some sort. So the idea of what cheaper means here is varies. But like on older machines, it was very common that you would, one common compiler optimization was to replace a multiply by a power of 2 with a shift. In APL, we would take, and I know we certainly did this in Sharp APL. The Apex compiler, APL compiler, does this too. If it sees a multiply and the arguments are Boolean, well, that just becomes an AND. Because now I don't have to do the multiply, and I get instant SIMD happiness. Min becomes an AND as well. Power becomes a greater than or equal, and all these things on the right. Watch this. There's my laser pointer. All these things on the right, we can do 32 bits at a time on those machines. So what we end up with as a result of doing this is we get simpler verbs, because I would rather do a greater than or equal than an exponentiation. I get SIMD operations, so I can do 32 bits at a time. We get rid of conditionals in a lot of these computations. Like, so example, in doing a max or a min, you would tend to have a conditional in there. You replace it with an and the conditional evaporates. Things run faster. That may, in turn, the elimination of the conditional may enable control flow optimizations, may introduce other opportunities for optimizations and so on. And finally, we stay in the Boolean domain. So the result, like in star, the result stays Boolean rather than going to floating point or something awful. So I already said that. Other things can happen. So let's look at some other examples. We looked at scalar functions right there. Let's turn to some of the structural and selection verbs. So concatenate, laminate, the list there, rotate, reverse, rank, from, and on and on. We've got these huge arrays of bits, and we'd like to do SIMD type stuff on them. A couple more, take, drop. Now the trick on this stuff is that these verbs have to handle array indices that may not be byte aligned, because you might have concatenating a 3-element vector, Boolean vector, to a 13-element vector, and they've got to be, the point where they join, they've got to be glued together in the middle of a byte. So we need some tools, fundamental tools, to make that easy to do. Those tools weren't always there. They tended to be ad hoc and written differently. And as usual, if you write a function to do this stuff, it becomes much simpler. In particular, it puts all your bugs in one place. And so we'd like to be able to do this stuff in a SIMD way. We'd like to be able to move a word at a time, or better if we can, on Boolean data. So there was something called LJW move in our APL. It was written by Luther Woodrum, which is where LJW came from. And so I took his stuff and cleaned it up. I cleaned it up and made it more general, and it did lots. So it did everything. It was all singing, all dancing, do data type conversions. But it was basically a stride one mover. Move. Oh, watch this. There. That's what it does. Ignoring the data conversion. Just basically pick up a vector of things that are in stride one, adjacent in ravel order, and move them, copy them somewhere else. Now, of course, Ken wasn't working in our group yet, because if he was, this never would have been called RBE move, because it doesn't move stuff, it copies stuff. The most important thing about RBE move was that it didn't corrupt array elements. LJW move would tend to smear stuff past the end of where it was supposed to write, so it was unsafe. So RBE move worked in SIMD mode whenever possible. It also exploited there's some essentially vector instructions on the 360 at the time that would let you move entire blocks, reasonably sized blocks of memory around, copy blocks of memory around. So it operates in SIMD mode whenever it can. As I said, it supports all type conversions and so on. So in terms of structure and selection verbs, something like rotate, it can copy an entire, so I'm working on the first axis here, so we can copy entire subarrays at one time. So in this case, it's a rank 3 array, and I'm interchanging the first two planes so I can move those. The cells are these 12 element, these 3x4 vectors. So if that's what I have it to begin with, up here, when I do the rotate, this entire plane can be moved as one block because those are contiguous elements. And that's sort of that's what we're going to be doing all through here. Around 1979, I was implementing nested arrays or enclosed arrays for Sharp APL. And in the course of this, I had to get my fingers into all these functions. So I took that as an excuse or a justification for re-engineering them and redesigning them for high performance at the same time. And I did last axis Boolean reversal a byte at a time. What it would do is it would basically treat each byte of Boolean data as an 8-bit index into a table, which would contain the reversal of the bits of those bit elements. And so in index operations, I'd basically get a factor of 8 speed up there, but they weren't aligned. Because you say, oh, I've got a 7-bit vector and I'm going to reverse it. When I get done with that byte reversal, I have to slide the thing over to align it. So it would then byte align it again a word and that would happen a word at a time. This was doing byte at a time for the reversal, and then a word at a time to shift it into where it belonged. Something called last axis, non-last axis operations copied entire cells as we saw before. And this is a plot that you'll see one of its neighbors on tomorrow. But this, so the, so this for a bunch of, these were last axis rotate on square matrices in the first axis, or axis 1. So this was the old algorithms, and then down here were were the stuff I wrote, and that's how many. That's basically time goes that way. So lower is better, and so that was pretty good stuff. I was happy with that. Reshape. Reshape allows element reuse. So if I do 8 reshape 1 0 0, I get 1 0 0 1 0 0 1 0. We're done. Well, how do we do this fast? Larry Breed had a lovely idea here. He just said, well, I'm going to copy the argument to the result, and then I'm going to catenate that result to itself, which would double its length. And if you do that enough times, turn 3, if you do it enough times, the tail of that, we assume the beginning of that vector the beginning of the result is going to be byte aligned. No matter what length you start with, by the time you do it 3 times, the tail end is byte aligned. And at that point, you just do an overlap smeared move to say, well, I'm going to copy from here to here until you get over there. And if the move works in the right order, it'll be safe. And there was an instruction on the 360 to let you do that. Other people, some other people, I think Dyalog in particular, they do the catenate trick, but I suspect partially because these overlap move stuff is a little dicey on some architectures. They just continue to concatenate the thing to itself until they get to the right size result, and that's it's equally effective. So let's turn to transpose. It's hard to think about transpose and say, okay, how am I going to do multiple bits at once on this? Well, the only 2 that I could come up with were this one. I've got unchanged trailing axes. So here I've got a 2 by 2 by 2 by 3 array, and I'm going to leave the last several axes in the same order. So we can do here, if I do a 1 0 2 3, the 2 and 3 axis, the 2 last axes are going to stay the same. So we can move globs of 6 elements at once, and in the Boolean case, well, I move 6 bits at once. Then I was talking with Jay Fote about this, and he pointed me at a book called Hacker's Delight, and it has a it's an elegant Boolean 8x8 Boolean transpose algorithm that it's kind of cute but scary. And what it does is it does 16 logical and shift operations on the ravel of this 8x8 matrix, and when you get done, it's transposed. So and the other thing you do is this perfect shuffle, which is this PDEP is I think one of these AVX something instructions on the newer Intel boxes. And effectively what it is a perfect shuffle, as you used to see on the APL t-shirts. And so what happened is you can get, this would also work on, it turns out it'll work on any power of 2. So if you've got a machine that's got more than 64 bits, like maybe it's a 256-bit registers, well, you could do larger. And so now Jay implemented this in some release or another of Dyalog APL, and he claims that he got and he had a customer that was quite happy with that factor of 10 speed up. So that's pretty good stuff. So I said the kernel generalizes to any power of 2, and okay, I guess there's something in the page. There's some functions in the paper that go into a bit more detail on this. When you're doing searching Boolean arrays, back in the dark ages, I rewrote index of and set membership to use subquadratic algorithms, and that was my first job at Sharp. I'd been hired to do I'd been hired to work on the IPS COBOL compiler, and my job was to brown thumb, and I was supposed to break the type conversion things, because COBOL had 1,000,002 data types and had, two-digit integers, or two-digit decimal numbers, 3-digit, 4 digits. It had probably signed Roman numerals, you name it, and on and on. And I did a couple of these by hand just to get a feel for it, and then Roger Moore, who I was working for, came over and said, "Okay, I see what you're doing. I think you better," because I was getting a feeling, sir, it's like, how am I going to write 1,000 test cases? And he said, well, you should use this, you should use APL to do this. And I said, okay, fine. But that's another story, which we'll talk about tomorrow. So this, I sped up epsilon and iota on all data types except reals at the time, got to them later. And effectively this way, in the Boolean domain, I would go and look up the left argument and find the first index of the first 0 and the first 1. If it was character, I would find the first index of each character, and those could be done in row alpha or less time, and then just index that table with the right argument, and we were done. So that was pretty good. Now, when we're doing this alpha iota 0, 1, I did a vector search for the first byte of interest in the left argument, and then a table lookup to get the bit offset into the byte. And speedup was excellent. I'm very happy with that. And while I was at it, I realized that there are some other things in the other place of the interpreter that we're interested in, saying, well, where's the first 1 in this row of this matrix, and so on. So I added entry points for the interpreter to use internally as well at the same time. Around that same time, Roger Moore was doing something. I can't remember what he was doing, but he was grousing about the performance of compression, and looked at it. And one of the things compress and expand have to do is to compute the number of ones. With a Boolean left argument to compress, it has to count the number of ones in left argument to decide whether it's the work is, or to decide the shape of the result. It turned out that computation was taking longer than the actual compression, because the part that did the second half of the job, the actual data moving part, was pretty slick. And I don't know who wrote that. At any rate, so he figured, okay, there's got to be a better way to do this. So what he did is he made a copy of the left, or pieces of the left argument, and then did there's a thing called the translate instruction, which is a vector SIMD operation on the 360. Effectively what it did is you gave it a table, and you pointed at some text, and it would replace the text by the character in the table corresponding to the index of that character in the alphabet, or in the machine's alphabet. And so that converted these Boolean values into population counts for each byte. Well, now he's got this piece of a segment of 124 bytes or less instead of having just the bits, he's now got in each byte the number of bits in that byte. And he then summed those a word at a time. So he was getting 4 8-bit adds for the price of one addition. And so he ended up with a four element partial sum in that register. And then when he got done, he did shift and adds to get to combine those four, to do a plus reduce on those four elements. The segment size is this funny 124 bytes thing, is the biggest value that you can use that will let you do these 4-byte sums without an overflow, an interbyte overflow. So pretty simple. And then Larry Breed saw this and effectively turned it into this thing, which he thought was a good APL haiku, because it becomes very clear what the algorithm is. The Rogers plus reduce Boolean code here was also used, at least for a couple of years. It was also used in or reduce and reduce, because it turned out just about always it was quicker to do the plus reduce and do a compare than it was to do the old reduction code. 1974, along comes Eugene McDonnell, and of course, whenever you see the word McDonnell here, you almost always see the word elegant next to it, because Eugene just did beautiful, beautiful things. So we came up with models of Boolean scan and reduction for all the relationals, and they were quite lovely. It was he generated a prefix, an infix, and a suffix expression for any particular scan, and the result was just the catenate of those. So it was very simple, straightforward code. Those expressions were generated based on where the first 0 or 1 appeared in each row of those arrays, and so they used my fast index of to do that. So we ended up with linear time, linear time, word at a time scans and reductions in the Boolean domain. This is good. Further on in, and this is something, I've lost this, and I don't know if anybody, there's a guy named John Heckman who produced, before the scan operators were introduced into APL, there were some user-defined functions kicking around that did scan. And they were attributed to a guy named John Heckman. I once had a copy of those on hard copy, and I think they're still in my library, but I can't find them because of the librarian has trouble. So if anybody has copy, can send me, has this kicking around, and can scan it in or take a photo of it and email it to me, that would be great. Because these are the earliest versions I've seen of these early scan functions. They're now, there were several people working, like some of the people working on the connection machine and a few other things recently on GPUs. The Heckman algorithms are being used in GPUs and things for scans now. They do not cite Heckman's work. I don't think he ever published it. It was just mythology in the biz. And the way it worked was recursive doubling. So here's a not equal scan, and it would do 2 log of the shape of the argument iterations over the argument. In this case, we're doing not equal scan, so it starts off with the argument, and then would do the not equals with the argument or the current result shifted by 1, 2, 4, 8, 16, and so on until you were done. So simple, very good APL code. Yes, it's iterative, but it only iterates 2 log n times. So it's very good stuff. Simple and clean. Well, what happens, of course, well, this whole thing happens The take and the drop are just those are all gonna be SIMD vectorized, even in an interpreter. The not equals is gonna happen a word at a time. So this whole thing, even an interpreter, will run quite well. I did a simple implementation of this on vectors only in C, and using 32-bit, it would iterate. It wouldn't do the whole vector at a time. It would do a word at a time, and then some fancy stuff about propagating the sign, or the propagating the last bit of the previous word's result into the current word. And it's dead, pretty bog standard code. I wrote it in about an hour or so, and it runs about 3 times faster than Dyalog's equal not equal scan. And the other thing is, it was 32 bits, and I said, well, I want to use 64 bits. So I converted to use 64 bits. It ran slower, and I didn't have time to figure out why that was, other than to see that the code that it generated was a lot more convoluted than I had expected. And also, I didn't see, there's no vectorization, but I didn't even attempt to do that because I had to get on an airplane. So there's still room for improvement there, I guess, is my point. Back in the early 70s, we always knew that Boolean inner products were slow, and as workspaces increased, we were no longer stuck with 32K workspaces. I think we had 48K. So huge. And Control Data Corporation was building a thing called the Star 100. It was a memory-to-memory supercomputer, and they wanted APL on it, and they hired. Okay, that's not true. Their customer wanted APL on it, and so they got in touch with us, and there were some people from CDC working on this APL interpreter, and a bunch of people from Sharp. Unfortunately, I would have loved to be part of this project, but it was ongoing when I joined the company, and I was not invited on that cruise. So I got to watch from the sidelines. The thing about the Star 100, it was a memory-to-memory machine. It didn't have registers or pipelines. It ran from memory to memory. So you had to have stride 1 access and long vectors to get good performance. So in a sense, just like APL interpreters, same thing. So they're trying to write inner product, and of course you write it the standard way, and it's doing this. Well, this is fine, that's stride 1. This is not. And it ran like dirt. So one or more of them came up with a variant on the matrix product algorithm, basically interchanging the loop order, and they got this nice stride 1 inner product algorithm. And I heard about this in passing, and I said, well, this would be really nice for Booleans. So I redesigned our inner product algorithm to use the star, what I call the star algorithm, and David Allen did the implementation of it. And here's basically what happened. If you stand back, okay, there you go. So here's your classic matrix product, inner product in APL, and as you can see, this is scalar, 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 scalar. We're not getting much array stuff happening here. This is bad. And we've got 3 levels of for loop nesting. Here's the star algorithm. So So it iterates. The outer two loops go over the number of rows in X and the number of columns in X. And there is no third loop. It's here. It's hidden. It's hidden inside. So we're dealing with a row of Z and a row of Z and a scalar from the left argument and a row of the right. So this is a stride one scalar vector thing going on here. And this is a vector-vector operation going on. So this is all good. This is good stuff. Not just, both for APL and for machines that like vectors. So this gives a good potential for speed up. The other point is that we've got this element from X. We only look at each element from X once. What that means is that, and then we're going to be applying it to a row of Y. So there's a couple of observations here. One is that if there's any type conversion involved, say I've got to convert from Boolean to real or something, because I'm doing money over here and who owns which over here. So the cost of that type conversion is amortized over this entire row. So any analysis you want to do here is cheaper. It also means that you can do some games with algebra on X, and it doesn't cost you very much. So we reordered the inner loops. As I said, we fetch each element of left argument once. The type conversion is no longer time critical, and any analysis of that X element is paid for over an entire row. And so let's think about this. As I said, we do scalar vector application of G for f dot G, and then the reduction step is in a vector-vector reduce. In the case of it being Boolean, we can do that. We can do that a word at a time. Similarly, we can do the reduction a word at a time. So things are faster already. The star APL model. This one. This is slow. This one is, what did I say, 90 times faster in APL. So you can do simple things to APL that make things make a difference, and vectorization is clearly one of those. Unfortunately, that APL model is still 30 times slower than the primitive. So implementers will still have a job. But let's look at what kind of optimizations we can do on here. So I've got XL and R0. Okay, so we're doing a Boolean inner product here. This same thing will work if that was a multiply and we're doing real numbers. Well, if XL is 0, XL and anything is all 0, or XL times anything is going to be all zeros. So that's the case. Well, then we know the temp is 0, and we don't even have to do the computation on G for that element. Furthermore, if XL is 1, then that's an identity, and that being this, the identity, and the result is just R0. So again, we don't do any computation on G. Then F is OR, and it has an identity element of 0. So if XL is 0, we can also skip the reduction on G. And if XL is 1, we do have to do the reduction, but we do it using R0. So in a sense, what this is giving us is a poor man's sparse array implementation. Anytime you hit a 0 in the left, it's going to be really quick. If you hit a 1, it's slightly more, but you've saved about half the cost. Gotcha. Thank you. And the kicker here, we came out with Sharp APL PC somewhere along the line here, and ran these Boolean inner products on Sharp APL PC, which was, we wrote a 370 emulator that ran the Sharp APL system, assembler code, and it beat APL2 in the mainframe. This happened in APL conference in Manchester, and Jim Brown was touting it, and I said, "Oh, here, try this." He wasn't very happy. So I think, and here's an interesting thing. We're changing subjects here. Control flow becomes data flow. This is good stuff. Booleans, for arithmetic, they let us replace if then else's by other things. So we do conditionals. So I want to give everybody whoever's getting paid less than tiny arrays of R. Well, rather than go through element by element saying, okay, if this element of S is less than that, then give the NAD, da da da. Instead, we just do this, and the whole thing is one big vector. I just take their salary and add R times that Boolean, and we're done. And Don Knuth calls this Iverson's convention for characteristics functions. This is the treating of relationals as producing zeros and ones instead of trues and falses or something, which are harder to add. And in the paper, there's a simple scan that does the same sort of thing for finding quoted text. And there's if you go to the ACM website, you can find a PLDI paper that I put together with Sven Bodo Schultz that does some good things here as well. If you can't find that paper online, or you just get in touch with me, and I'll send you one. I'm running short on time, so I'm going to crank through these. We can do sort. We can do fairly quickly. It would use Rogers plus reduce Boolean function here for the first phase. And the second phase just sloshes stuff around. It's pretty simple. Upgrade is not as nice, but it's not stunningly SIMD either. So I don't have any bright ideas, or others may have brighter ideas. And these byte-oriented algorithms, and word-oriented algorithms, you have this beautiful thing that's handling the middle of this row of a matrix, going bang, bang, bang. And then you get to the end of the row or the beginning of the row, and you got this little mess. It's like painting the corners of a room. There's always little things, and these are a pain. The algorithmic beauty's gone. They're slower. So you'll see. Well, this works at a gazillion times faster on a vector, and you turn it into do the same thing on a 10-row matrix, and it runs like 10% slower or something. That's why. I'm not going to. I'll just say that these shards are the things that start or end in the middle of a word. That's all I have to say. I owe thanks to a lot of people here who contributed to ideas and stuff on the paper. Jim Brown, Larry Breed, Walter Phil, who's Jay Fode, Roger Huey, Roger Moore, and Bob Smith. All good ideas. Any timings you see here were done on Dyalog 15.0. And I'd like to offer my sincere thanks to the British APL Society, because they provided me with some financial assistance to help me get over here. And I appreciate that thought. Thank you.